Something has been found at the edge of the observable universe, a structure so large that light from one end will never, in the lifetime of this universe, reach the other end. Scientists have measured it. They have run the statistics. They have checked the numbers against the rules of physics that say structures like this cannot exist, and the numbers keep coming back the same way. If this thing is real, it should not be there. The universe should not have been old enough, or powerful enough, or organized enough to build it. But there it is in the data, 10 billion light years of something, sitting in the sky in the direction of two constellations named for ancient heroes and refusing to go away. Tonight, we follow the scientists who found it, the ones who challenged it, and the instruments now being built to settle the question once and for all. If this is the kind of journey you want more of, the universe's deepest puzzles told slowly, patiently, take a moment to like this video and subscribe to the channel. Your support is genuinely what makes these explorations possible. Take a slow breath and let yourself settle in. In 3, 2, 1, liftoff. There is a kind of order to the universe that took us a very long time to see. Not order in the way we usually mean it when we look up at the night sky, not the familiar patterns of the constellations, those ancient dot-to-dot pictures our ancestors drew across the dark to help themselves feel at home. That kind of order is an illusion, a trick of perspective, stars at wildly different distances that happen to line up from our particular vantage point on one small world orbiting an ordinary star. No, the order I am talking about is something deeper and stranger and far more beautiful than that. It is the order of the universe itself when you step far enough back to see it whole, when you pull away from individual stars and galaxies the way a pilot pulls away from the runway, leaving behind the details until only the largest shapes remain. And what remains, when you have gone far enough, is something that looks less like a scattering of light and more like the architecture of an immense ancient building. Astronomers call it the cosmic web. It is the large-scale structure of the universe, the skeleton, the framework, the grand organizing principle that arranges the matter of the cosmos, not randomly, but in an intricate pattern of sheets and filaments and enormous hollow voids. Imagine the foam that forms when you lather soap between your palms. Those bubbles pressing against each other, their surfaces studded with small beads where the soap concentrates, that is roughly what the universe looks like on its largest scales. The voids are the empty interiors of the bubbles. The filaments are the thin soap walls between them. And the galaxy clusters, those dense swarms of hundreds or thousands of galaxies bound together by gravity, are the glittering beads at the intersections where the walls meet. Spread that soap foam across something roughly 93 billion light-years in diameter. Let each bead contain 1,000 galaxies. Let each galaxy contain hundreds of billions of stars. And you will have begun, only just barely begun, to appreciate what the cosmos assembled for itself in the roughly 13.8 billion years since the universe began. This structure was not always visible to us. For most of human history, and for most of the history of astronomy, we could not see it at all. We saw individual stars with the naked eye and imagined their patterns meant something. We built the first telescopes and began to see that what the eye took for faint smudges were in fact entire other galaxies, vast island universes of their own, each containing billions of suns. That revelation arriving fully in the 1920s, when the American astronomer Edwin Hubble confirmed the true nature and distance of those fuzzy patches, was staggering enough on its own. But the universe had barely introduced itself. What lay beyond the galaxies themselves, the way they were arranged across the vast darkness, the architecture that connected them and organize them into something coherent that was still completely invisible to us, because we lacked both the instruments and the mathematical tools to map it. The breakthrough began slowly in the second half of the 20th century, as astronomers started measuring not just the positions of galaxies in the sky, but their distances from us. Distance is everything in cosmology. Because the sky is a flat projection, you can see that two objects appear close together without knowing whether one is a few million light-years away and the other is 3 billion light-years away, superimposed by accident. To build a true three-dimensional map, you needed to add that third dimension, and the tool that made it possible was the redshift. When a galaxy moves away from us, which most galaxies do, because the universe is expanding, its light stretches out toward the red end of the spectrum. The faster the recession and the farther the galaxy, the redder its light becomes. By measuring that reddening carefully, astronomers could calculate distances with reasonable precision and begin placing galaxies at their true positions in three-dimensional space. What those maps revealed, once astronomers had gathered enough data, was the cosmic web. Survey by survey, the pattern emerged from the data. The Cepheid-2 survey in the 1980s produced the first clear glimpse of the great walls and voids that define cosmic architecture. The Sloan Digital Sky Survey, beginning in the year 2000, extended that mapping to cover nearly a third of the entire sky and hundreds of millions of galaxies, producing images of the cosmic web detailed enough to make it look like something you could reach out and touch. Great luminous threads of galaxies stretching across hundreds of millions of light-years, curving away from one another to enclose vast dark spaces as empty as anything in the observable universe. The cosmic web is not an accident. It is the direct consequence of conditions set at the very beginning of time, specifically tiny variations in density that existed in the first fraction of a second after the Big Bang. In those first moments, the universe was not perfectly uniform. There were regions slightly denser than average, regions slightly emptier, not by much, by perhaps 1 part in 100,000. Those variations were too small to see, too small to have any obvious significance. But gravity is patient. Over millions of years, then hundreds of millions, then billions, the slightly denser regions pulled in material from their surroundings. They grew denser still. They attracted more material. Meanwhile, the slightly emptier regions grew emptier as their matter drained away toward the concentrations forming all around them. Over cosmic time, this process, gravity, amplifying tiny initial differences into enormous final structures, built the cosmic web we observe today. The filaments, the sheets, the clusters, the voids, all of it traceable directly back to quantum fluctuations so small they would fit in something smaller than an atom, amplified across 14 billion years into the architecture of the observable universe. This is not a simple idea, but it is a beautiful one. And it is the foundation on which everything we are going to talk about in this video rests, because it is precisely this understanding of how large-scale structure forms that makes the object at the center of our story so deeply, fundamentally troubling. Before we get to that trouble, we need to understand one more idea, and it is perhaps the most important idea in all of modern cosmology. It is called the cosmological principle. At its heart, the cosmological principle is a statement about fairness. Cosmic fairness, you might say. It holds that, on sufficiently large scales, the universe looks the same from anywhere. It is homogeneous, meaning it has the same average properties everywhere, the same average density of matter, the same average density of energy. And it is isotropic, meaning it looks the same in every direction, no preferred axis, no special orientation. A being living in a galaxy cluster on the opposite side of the observable universe, looking out in every direction, would see a cosmos statistically identical to the one we see from our corner of the Milky Way. The cosmological principle is not something astronomers simply made up because it was convenient. Though it is certainly convenient, it simplifies the mathematics of cosmology enormously. It has been tested by observation, over and over, across enormous ranges of scale and distance. The cosmic microwave background radiation, the faint afterglow of the Big Bang itself, still washing through the universe after 13.8 billion years, is perhaps the most powerful test of the cosmological principle that exists. Maps of that radiation, produced by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft, show a sky that is extraordinarily uniform. Temperature variations in the background radiation, which correspond to density variations in the early universe, amount to only a few millionths of a degree from one spot to another. That is a universe that was, at the time that light was released, staggeringly smooth and even, and the cosmic web that grew from those tiny seeds reflects that smoothness, at least when you average over large enough volumes. How large is large enough? That is the crucial question. The cosmic web is, after all, not perfectly uniform. It has structure. It has filaments and voids. Those features exist on scales ranging from tens of millions of light-years, for individual galaxy groups up to hundreds of millions of light-years, for the largest confirmed superclusters and great walls. But the prediction of standard cosmology, the prediction of the framework called lambda cold dark matter, which is the consensus model that cosmologists use to describe how the universe evolved, is that above a certain scale, roughly 1 billion light-years, the clustering of galaxies should smooth out completely. You might still find structure at 500 million light-years. At 1 billion light-years, it should be fading. At 2 billion light-years and beyond, the universe should look, in any statistical sense that matters, perfectly uniform, the same everywhere, to any measurable degree. That is the prediction. That is what the cosmological principle demands at large scales. And for a long time, through the discovery of the Sloan Great Wall, at 1.3 billion light-years in 2003, through the mapping of superclusters, at various scales, cosmologists were willing to believe the universe was playing by those rules. Even when the observations were beginning to push the limits, they were willing to believe that, at least, until a team of astronomers began looking at something entirely different from galaxy surveys, something faster, brighter, and vastly farther away than any galaxy we could photograph directly. They began looking at gamma-ray bursts. To understand why gamma-ray bursts matter to the story of the universe's large-scale structure, you first need to understand what they are. Gamma-ray bursts are the most energetic explosions known to science. They are brief, lasting anywhere from a fraction of a second to several minutes, and during that brief time, they release more energy than the sun will radiate across its entire 10 billion year lifetime. They are caused by cataclysmic events, the collapse of a massive star at the end of its life into a neutron star or a black hole, or the merger of two neutron stars spiraling together under gravity until they finally touch. Either way, the result is an explosion of such ferocity that the gamma rays it releases can be detected across billions of light-years of space. When NASA's Swift satellite detects a gamma-ray burst, and it detects perhaps several hundred per year, it is often seeing light from an event that occurred before the sun existed, before the Earth existed, sometimes before the Milky Way had fully assembled itself into the galaxy we inhabit today. There is something important about that. Gamma-ray bursts require massive stars to produce them. Massive stars require dense, star-forming galaxies to form within, which means that wherever a gamma-ray burst occurs, there is almost certainly a substantial concentration of matter, a galaxy cluster, a region of active star formation. If you map enough gamma-ray bursts across the sky, you are, in effect, making a rough map of where mass concentrates in the distant universe. It is not a perfect map. Gamma-ray bursts are not uniformly distributed by mass. Some galaxies produce more than others, depending on their chemistry and their history. But the broad principle holds. Clusters of gamma-ray bursts are traces of clusters of matter. And this is precisely the insight that a Hungarian astronomer named István Horváth and his colleagues brought to bear on one of the largest questions in modern cosmology. Horváth had spent his career studying the statistical properties of gamma-ray bursts, how they were distributed across the sky, how they were distributed in time, what patterns their distances and positions revealed about the universe. Working from Budapest at the National University of Public Service, he and his collaborators Zsolt Bagolai at Eötvös Loránd University and John Hakila at the College of Charleston in South Carolina began applying careful statistical tests to the catalogue of gamma-ray bursts detected by the SWIFT satellite, a catalogue that by 2013 had grown rich enough to start yielding answers to questions about large-scale structure. In November of that year, their analysis produced a result that stopped them in their tracks. Looking at a subset of gamma-ray bursts at redshifts between roughly 1.6 and 2.1 meaning light that had been traveling toward us for approximately 10 billion years, emitted when the universe was only about 3.5 billion years old, they found something that should not have been there. In one patch of sky, roughly 45 degrees wide, spanning the constellations Hercules and Corona Borealis, 14 out of 31 gamma-ray bursts in that redshift range were clustered together, not nearby in the sky, the way random chance might occasionally arrange a few objects, clustered in a way that the statistical tests found extraordinarily hard to attribute to chance. The nearest neighbor test found significant concentration. The bootstrap point radius method found it again. The Kolmogorov-Smirnov test confirmed it. The probability that this clustering was the result of random distribution, the team calculated, was approximately 1 in 180,000. That is not a borderline result. That is a signal. And what that signal implied, if the gamma-ray bursts were truly tracing an underlying concentration of matter, was a structure of incomprehensible scale. A wall of galaxies, or a filament, or some other vast aggregation of matter, stretching somewhere between 6 and 10 billion light-years across, possibly larger, possibly much larger. They named it the Hercules Corona Borealis Great Wall. Sit with that name for a moment. The Hercules Corona Borealis Great Wall, named as astronomical objects so often are, for the region of the sky where we see it from our particular vantage point on Earth, in the direction of two ancient constellations, Hercules, the great hero of Greek mythology, and Corona Borealis, the northern crown. There is something fitting in that naming, because what Horváth and his colleagues had potentially found was something that dwarfed any human story ever told, any monument ever built, any empire ever raised, by a factor so enormous that the numbers required to describe the comparison are themselves barely comprehensible. But before we can fully appreciate what the discovery meant and why it was so troubling, we need to understand just how carefully the cosmological principle had been built and how much evidence had gone into it, because the weight of what the wall challenged is inseparable from the weight of what had come before it. Think about the history of how we came to understand cosmic structure. For most of human civilization, we had no conception of deep space at all. The stars were simply there, fixed in the sky, permanent and unchanging, the backdrop against which the wandering planets moved. Even after Galileo and then Newton gave us the tools to understand that the sun was a star, and that the other stars were distant suns, the true scale of the universe remained invisible to us. The Milky Way was, for a long time, thought to be the entirety of the cosmos, a vast system, certainly, but finite, and surrounded by empty darkness. When the existence of other galaxies was confirmed in the early 20th century, the universe expanded overnight in our imaginations by a factor that is literally incalculable. There were not just stars. There were galaxies, each containing hundreds of billions of stars, and there were so many of them that the current best estimate puts the total in the observable universe at somewhere around 2 trillion. 2 trillion galaxies. And from all of that, from decades of mapping their positions, measuring their distances, cataloging their properties and their velocities and their clustering patterns, from all of that data, cosmologists built a picture of the universe as something that, on its largest scales, was smooth and even and governed by predictable physical principles. The cosmic microwave background confirmed it. The pattern of galaxy clustering confirmed it. Computer simulations of how the universe evolved from its earliest moments reproduced the cosmic web we observe with remarkable accuracy. The lambda cold dark matter model, which describes a universe filled with ordinary matter, cold dark matter, and the mysterious dark energy driving the accelerating expansion, matched the observations on scale after scale after scale. It was not a perfect model. No model ever is. But it was the best model human science had ever produced for describing the structure and evolution of the entire observable universe, and it rested at its foundation on the cosmological principle: the universe is, at large enough scales, the same everywhere and in every direction. The problem with the Hercules Corona Borealis Great Wall is not merely that it is large, it is that it is too large. It is so large that the cosmological principle that bedrock assumption cannot comfortably survive it if the wall is real. The theoretical limit for coherent structures in a universe governed by lambda cold dark matter is usually cited at around 1 billion light-years, or roughly 1.2 gigaparsecs. Some recent analyses have pushed that boundary somewhat, finding that the standard model may tolerate patterns at somewhat larger scales than once assumed. But 10 billion light-years is not a few percent larger than the theoretical limit. It is 8 times larger. It is not a gentle challenge to the cosmological principle. It is a direct confrontation. And the confrontation runs deeper than the size alone. There is a time problem. A problem that, in some ways, is even more unsettling than the sheer extent of the structure. We will return to that time problem in fuller detail later in this video, because it deserves the space to be explained properly. But even here, at the beginning of this story, it is worth understanding what the problem is in its simplest form. The wall, if it exists, sits at distances corresponding to a time when the universe was roughly 3.5 to 4 billion years old, relatively young in cosmic terms. At that age, the universe simply had not had enough time, under the known rules of gravity and structure formation, to assemble something 10 billion light-years across. Gravity is powerful, but it is not instantaneous. Structure grows at a rate governed by physical laws, and those laws, applied to the conditions of the early universe as we understand them, cannot produce a 10 billion light-year object in the time available. Something either is missing from our understanding of how the universe works, or the wall is not what the data appears to suggest. That is the mystery at the heart of this video. And to tell it properly, we have to begin where all good stories of scientific discovery begin, not with the answer, which we do not have, but with the moment the question first arose. Not with the wall itself, which may or may not be what it appears, but with the framework that the wall, if real, would shatter. We have to begin with the order, the beautiful, hard-won, carefully tested order that the universe appeared for so long to obey. Across millions of telescopic hours of observation, across mountains of data gathered by instruments from mountaintop observatories in Chile and Hawaii and New Mexico to spacecraft orbiting hundreds of miles above the Earth, the cosmos revealed its pattern. The cosmic web emerged from the data like a photograph, developing in a dark room, slowly at first, then with increasing clarity and resolution, until the structure was unmistakable. Filaments of galaxies stretching for hundreds of millions of light-years. Great sheets of galaxies, flattened by the dynamics of gravitational collapse, like enormous pancakes made of 100,000 galaxies each. Voids not empty in the sense of containing nothing, since dark matter and faint galaxies and thin wisps of gas thread even the emptiest regions, but empty in the sense that really matters cosmologically, which is to say, underdense by 20, 30, 40% compared to the average. These voids are as important to the story of the universe as the filaments that surround them. They grew as their matter drained away. They expanded as the universe expanded, and as dark energy pushed space apart, the voids grew faster than everything else, becoming the dominant feature of the cosmos by volume, even as the filaments and clusters remained its dominant feature by mass and luminosity. The largest confirmed structures within the cosmic web had been growing in scale as observation improved. The Cepheid Great Wall, discovered in 1989, stretched across roughly 500 million light-years. The Sloan Great Wall, identified from the Sloan Digital Sky Survey data in 2003, extended to approximately 1.4 billion light-years, a scale that already pushed at the edges of what the cosmological principle was supposed to allow, and which generated genuine debate about whether the standard model needed modification. But the Great Wall of the Sloan Survey was a sheet of galaxies seen in optical light, mapped directly, its component galaxies photographed and measured individually. It was, in the end, explicable within the bounds of what cosmologists were willing to accept. It was large, but not impossibly large. It was at the edge of the permitted, not clearly beyond it. The Hercules Corona Borealis Great Wall, if real, would be in an entirely different category. Not large, but just barely acceptable. Not at the edge of what the cosmological principle can tolerate. Beyond it, far beyond it, by a factor that leaves no comfortable room for the standard model to breathe. And so the story that we are about to follow is, at its core, a story about what happens when the universe appears to have broken its own rules. It is a story about a team of scientists who found something in the data that they were not looking for and could not immediately explain. It is a story about the specific, careful, painstaking work of science, the statistical tests run and rerun, the objections raised and considered and partially answered. The instruments proposed and built and aimed at the sky in the hope of settling the question one way or another. It is a story about what we do when observation and theory do not agree, and we do not yet know which one to trust. And it is a story about the universe itself, which has been assembling its structures across billions of years without once consulting our models of what it was supposed to do. There is a quality of quiet in the deep universe that the cosmic web somehow captures. When you see the visualization that astronomers produce from their survey data, the long, luminous filaments of galaxies curving through the dark, the cavernous voids between them, the whole thing looking something like a brain's neural network laid out across billions of light years. There is a stillness to it that is not what you might expect from a description involving explosions and gravity and billions of stars. It is still because the timescales dwarf anything we can feel. The cosmic web did not assemble in a hurry. It assembled across the full span of cosmic history, one tiny gravitational nudge at a time, accumulating its structure the way a river delta accumulates sediment by the slow, patient, essentially relentless operation of physics across almost incomprehensible stretches of time. And the Hercules Corona Borealis Great Wall, if it is what it appears to be, is a structure that was somehow assembled faster than that patient process should have allowed. That is the core of what makes it so fascinating and so unsettling, not just its size. Its existence at a time when, according to our best models, it should not yet have had time to be. We are going to follow that mystery closely. We are going to look at the data that Horvath and his team assembled, the statistical tests they ran, the objections the scientific community raised, and the answers incomplete, honest, still contested, that the evidence has produced so far. We are going to look at the new instruments now trained on the deep sky, including the most detailed map of the cosmic web ever produced, released just months ago from the James Webb Space Telescope, and the forthcoming satellite mission that researchers believe may finally settle the question of whether the Hercules Corona Borealis Great Wall is the largest structure in the observable universe, or the largest pattern in a limited and imperfect data set. But first, we need to understand the order that came before it. The careful architecture of what we knew, the elegant, testable, repeatedly confirmed framework of how the universe organizes its matter at large scales. Because that is the thing the wall challenges, not some fringe idea, not some loosely held hypothesis, the deepest load-bearing assumption of modern cosmology. And you cannot fully grasp what it means to challenge something like that until you understand why it was trusted in the first place. The trust was earned across generations of work. The cosmic microwave background, first detected accidentally in 1965 by Arno Penzias and Robert Wilson at Bell Telephone Laboratories in New Jersey. While they were troubleshooting a microwave receiver, they could not get quiet. Turned out to be the echo of the Big Bang itself, radiation that had been traveling through space for 13.8 billion years, a fossil of the universe's first moment of transparency. When later missions mapped that radiation across the full sky with exquisite precision, they found exactly what the cosmological principle predicted: extraordinary uniformity. Not perfect uniformity, those tiny variations, those ripples of 1 part in 100,000, were the very seeds of all structure we observe today, and their pattern matched the predictions of lambda, cold, dark matter, with remarkable precision. But uniformity at the level that matters, homogeneity at the largest scales, the universe looking the same, statistically, in every direction. The galaxy surveys confirmed it, at lower redshifts. The clustering of galaxies on scales of a few 100 million light-years matched the predictions. The baryon acoustic oscillations, those frozen sound waves from the early universe, imprinted on the distribution of galaxies as a characteristic scale of roughly 500 million light-years, appeared exactly where they should. A reliable ruler stretched across the cosmos, at scale after scale, distance after distance, always pointing back to the same underlying cosmology. Computer simulations running on some of the most powerful supercomputers ever built reproduced the cosmic web from first principles, starting from the density variations of the early universe and evolving them forward in time under the known laws of gravity and dark energy, producing a simulated cosmos that matched the observed cosmos in its statistical properties across an enormous range of scales. That is the weight of what the Hercules Corona Borealis Great Wall confronts. Not a guess, a framework confirmed by independent evidence from a dozen different directions, tested across cosmic time, refined across half a century of observation. A framework that has made predictions and watched those predictions confirmed. A framework that has earned, more than almost any other in science, the right to be called a genuine description of how the universe works. And then, in the data from a satellite tracking the most violent explosions in the cosmos, a cluster of signals appeared in one patch of sky that the framework cannot comfortably accommodate. The universe had apparently been doing something the models said it could not do. And the scientists looking at those signals did what scientists do. They checked the data again, ran the tests again, consulted the literature, wrote the paper, and sent it out into the scientific world to be examined. What happened next, and what is still happening now, more than a decade later, with better data and better instruments and better simulations than Horvath's team had available in 2013, is the story we are about to tell. The data arrived the way most important discoveries do, not in a moment of theatrical revelation, but in the patient accumulation of numbers that refused to behave the way they were supposed to. In November of 2013, the team that included Istvan Horvath, Zsolt Bagely, and John Hakila had been working through a catalogue of gamma-ray bursts detected by NASA's SWIFT satellite over a span of roughly 15 years. SWIFT had been launched in November of 2004, specifically to hunt these extraordinary explosions, to catch them in the act, measure their properties, and relay their positions to ground-based observatories fast enough for follow-up observations before the afterglow faded. By 2013, it had compiled one of the richest gamma-ray burst catalogues in existence, and that catalogue had become a resource, not just for studying the bursts themselves, but for using them as tracers of the distant universe in ways that their discoverers had not originally imagined. The SWIFT satellite was not designed to map cosmic structure. That was not its mission. Its mission was to detect the most violent explosions in the sky and gather enough data, quickly enough, that scientists could understand what produced them. But science has a long tradition of finding its most important answers in data gathered for entirely different purposes. The cosmic microwave background was discovered by two scientists at Bell Telephone Laboratories in New Jersey, who were trying to eliminate interference from a large antenna. What they thought was a nuisance turned out to be the echo of the Big Bang. The expansion of the universe was discovered by Edwin Hubble while he was simply cataloging the distances and velocities of galaxies. Discovery has a way of hiding in the corners of data collected for other reasons, waiting for someone to ask the right question of the numbers. The right question, in this case, was whether the gamma-ray bursts in Swift's catalogue were distributed uniformly across the sky, as they should be if the universe is homogeneous on the scales those bursts were tracing, or whether they clustered in ways that suggested underlying structure. The cosmological principle predicts uniformity. If it holds, then gamma-ray bursts at any given redshift range, meaning any given distance from us, should appear roughly equally distributed in every direction, with only statistical fluctuations around that average. If it does not hold, if the universe retains meaningful structure at the distances gamma-ray bursts occupy, then the bursts should cluster, concentrated in the directions where the great concentrations of matter lie. Horvath and his colleagues divided the Swift catalogue into redshift bins, groups of bursts, at roughly similar distances, and asked, for each group, whether the distribution across the sky was consistent with randomness. Most of the bins were well behaved. At lower redshifts, the bursts were approximately uniformly distributed, as expected. At higher redshifts, where the sample sizes grew thin and statistical noise dominated, nothing definitive emerged. But at redshifts between approximately 1.6 and 2.1, a range corresponding to distances of roughly 9 to 11 billion light-years, a time when the universe was between 3 and 4 billion years old, the distribution was not random, not even close to random. A cluster of 14 out of 31 gamma-ray bursts in that redshift range was concentrated within a single region of sky, roughly 45 degrees across, in the direction of the constellations Hercules and Corona Borealis. 45 degrees is a large patch of sky. To put it in terms of something familiar, if you stand outside on a clear night and hold your fist at arm's length, a single fist covers roughly 10 degrees of arc. The clustered region that Horvath's team identified was roughly as wide as 4.5 fists held side by side, a substantial fraction of the visible sky. In one sense, that is reassuring. This is not a microscopic anomaly detectable only by the most sensitive instruments. In another sense, it is deeply unnerving, because it means the structure implied by the clustering, the structure needed to explain why so many gamma-ray bursts are concentrated in that one region, would have to be truly enormous to subtend that kind of angle at those distances. The team ran 3 statistical tests. Each one was designed to ask, in a slightly different mathematical way, the same fundamental question: is this clustering consistent with random chance? The nearest neighbor test measured how close, on the sky, each gamma-ray burst in that redshift range was to its neighbors, and compared that distribution of separations to what would be expected from a random, uniform distribution. The result was significant. The bursts were closer to their neighbors than chance would predict, indicating genuine clustering. The bootstrap point radius method took a different approach, asking what fraction of the sky would need to be selected at various angular sizes to contain a disproportionate share of the observed bursts. Again, the result was significant. A region covering roughly 15 to 25% of the sky contained nearly half of all the bursts in that redshift range. The Kolmogorov-Smirnov test, a classical tool of statistical analysis that measures how different an observed distribution is from an expected theoretical one, confirmed the finding a third time. And when the team combined all 3 results to estimate the overall probability that the clustering was a random fluctuation, the answer came back at approximately 1 in 180,000. In statistical terms, this is well above the threshold that scientists typically use to call a result significant. It is not merely suggestive, it is compelling. 1 in 180,000. It is worth staying with that number for a moment, because it is easy to hear probabilities and let them slide past without fully grasping what they mean. If you were shuffling a deck of cards and you dealt yourself a royal flush, the rarest possible hand in poker, the odds against that happening by chance are roughly 1 in 650,000. This result was, statistically, more than 3 times more likely than that. Put another way, if you ran this kind of analysis on 1,000 different data sets drawn from a truly random and uniform distribution of gamma-ray bursts, you would expect to see a clustering this strong approximately 5 or 6 times. Not 0 times statistics is not magic, and rare events do occasionally occur, but 5 or 6 times in 1,000, which means that if the clustering in the Swift catalog were purely a fluke of chance, we would be looking at one of the more unusual statistical flukes that a gamma-ray burst catalog was likely to produce. That is possible. It is not impossible, but it is the kind of result that demands a physical explanation. The physical explanation that fit the data was a structure, a massive, extended concentration of matter in the direction of Hercules and Corona Borealis, sitting at the redshifts where the clustering appeared, large enough to boost the rate of gamma-ray bursts, and therefore of star-forming galaxies, and therefore of massive stars, and therefore of the kinds of explosive stellar deaths that produce gamma-ray bursts within that region of space. The team estimated the structure's size from the angular extent of the clustering on the sky and from the redshift range over which the clustering appeared, and what they arrived at was genuinely difficult to absorb. The structure appeared to extend across approximately 6 to 10 billion light-years. The most commonly cited figure in the scientific literature is approximately 10 billion light-years. That is roughly the length of the observable universe from one side to its center. That is a structure spanning roughly 10% of the diameter of everything we can see in any direction, no matter how powerful our telescopes. To help carry the scale of that figure, consider the largest structure that had been previously known and reasonably well confirmed, the Sloan Great Wall, identified in 2003 from the Sloan Digital Sky Survey data. The Sloan Great Wall was already considered controversial when it was found, because it was approximately 1.4 billion light-years long and sat at the edge of what the cosmological principle was supposed to allow. The wall had generated genuine discussion in the cosmological community about whether it truly violated the predictions of the Standard Model, or whether it was just barely within the range of structures that could form under lambda-cold, dark matter given the right initial conditions. Most researchers eventually concluded that it was borderline but not clearly impossible, that the cosmological principle survived the Sloan Great Wall, if only narrowly. The Hercules Corona Borealis Great Wall, if the interpretation of the gamma-ray burst clustering were correct, would be roughly 7 times longer than the Sloan Great Wall. It would not be at the edge of what the Standard Model can accommodate. It would be far beyond it, in a region of scale that the cosmological principle, as conventionally understood, does not allow. The team published their findings in 2014 in the journal Astronomy and Astrophysics. The paper was careful in the way that good science is careful. It presented the statistical analysis in full, acknowledged the limitations of the gamma-ray burst tracer method, discussed alternative explanations, and concluded that the most natural interpretation of the data was an underlying concentration of matter at the relevant redshifts. John Hackler, one of the co-authors, later spoke publicly about the result in terms that conveyed both the excitement and the discomfort it produced. He had expected the structure to be too big to exist, he said, and in a precise sense, that is exactly right. Under the standard model of cosmology, a structure of this scale should not exist. The universe should not have been able to build it in the time available, and yet the data appeared to say that it was there. The scientific community responded to the paper the way it responds to all extraordinary claims, with scrutiny. This is not a criticism of the process. Scrutiny is the process. When a result challenges something as fundamental as the cosmological principle, the appropriate response is to examine it from every angle, test every assumption, look for every possible alternative explanation, and demand that the evidence be strong enough to survive all of those challenges before the conclusion is accepted. That process, applied to the Hercules Corona Borealis Great Wall, produced a rich and still ongoing scientific debate, one that has clarified certain things while leaving the central question genuinely unresolved. The first and most important class of objection concerned the gamma-ray burst tracer method itself. Gamma-ray bursts are luminous enough to be detected at enormous distances, which is precisely why they are useful for probing the structure of the early universe. But they are not perfect tracers of matter. The connection between gamma-ray bursts and the galaxies that host them is real but complicated. Gamma-ray bursts of the long variety, the kind most useful for cosmological mapping, produced by the collapse of massive stars at the ends of their lives, tend to occur preferentially in galaxies that are actively forming stars at high rates, and in galaxies with relatively low metallicity, meaning galaxies with relatively small amounts of elements heavier than hydrogen and helium. This preference means that gamma-ray bursts do not trace all galaxies equally. They trace a specific subset of galaxies with particular properties, and that subset may be distributed differently across the sky than the total galaxy population, introducing biases into the picture that the clustering analysis must somehow account for. Additionally, the detection of gamma-ray bursts is not perfectly uniform across the sky. NASA's SWIFT satellite has a finite field of view and cannot observe the entire sky simultaneously. Its pointing history, where it has been aimed and for how long, at different periods creates an uneven sampling of the sky, such that some regions have been observed more thoroughly than others. If the satellite happened to observe the Hercules Corona Borealis region more frequently than other parts of the sky during the period when it was detecting bursts in the relevant redshift range, that asymmetry in observational coverage could, in principle, create the appearance of clustering where none existed. The team was aware of this concern and addressed it in their analysis, arguing that the observational biases in the SWIFT catalog were not sufficient to explain the clustering they observed. But the concern was legitimate, and it remained a thread that critics continued to pull. A second class of objection concerned the sample size. 31 gamma-ray bursts, distributed across a wide redshift range, and then subdivided into angular patches of sky, is not a large number. Statistics derived from small samples can be unreliable in ways that statistics derived from large samples are not. A cluster that appears anomalous when you have 31 data points might look perfectly ordinary when you have 300. This is not a defect of the original analysis. The team used the data they had, and they used it with appropriate statistical tools. But it meant that the result was provisional in a way that a result based on a much larger catalog would not be. The question of whether the clustering would persist or dissolve as the gamma-ray burst catalog grew larger was one that only time and more data could answer. A third consideration, less an objection than a complication, was the question of what the clustering was actually tracing. Gamma-ray bursts occur in galaxies, and galaxies trace matter. But matter, at the distances where the Hercules corona borealis signal appeared roughly 10 billion light-years away, cannot be seen directly in optical surveys. With the instruments available in 2013, we cannot photograph those galaxies the way we can photograph the galaxies in the Sloan Great Wall. We are inferring the existence of a concentration of matter from the distribution of extremely energetic events that we believe, with good physical justification, tend to occur in regions of high mass density. That inference is well grounded. But it is an inference. The structure itself, the galaxies, the dark matter, the filaments remains. For now, beyond the reach of direct imaging, the team's response to this collection of objections was to do more work. In 2015, Horvath, Bagoli, Hakila, and a fourth colleague named L. Victor Toth published a follow-up paper in the same journal, using an expanded catalogue of gamma-ray bursts that included additional data from the BATSI instrument, which had operated aboard NASA's Compton Gamma Ray Observatory in the 1990s, as well as bursts from the Fermi Gamma Ray Space Telescope, which had been launched in 2008 and had been quietly building its own catalogue of bursts in the years since. The expanded data set allowed the team to test whether the clustering persisted when more bursts were included, to ask, in effect, whether the original result was a statistical artifact of a small sample or a genuine feature of the large-scale distribution of gamma-ray bursts at high redshift. The answer was that the clustering persisted. Not necessarily at precisely the same statistical significance as in the 2014 paper. The numbers shifted somewhat as the catalogue changed, but the signal remained robust enough that the team felt confident, reaffirming their original interpretation. There was something in the direction of Hercules and Corona Borealis at redshifts between 1.6 and 2.1. What exactly that something was remained uncertain, but the statistical signal appeared to be real. That 2015 paper strengthened the case for taking the Hercules Corona Borealis Great Wall seriously as a scientific object of study, rather than dismissing it as a fluke. But it did not settle the debate. The debate in the scientific literature continued, with different groups applying different statistical techniques to the SWIFT catalogue and arriving at somewhat different conclusions about the significance of the clustering. Some analyses found the clustering highly significant. Others found the statistical tests used by Horvath and colleagues to be sensitive to specific choices about how to define the spatial bins, and argued that, with different choices, the signal was less compelling. A 2020 study by a researcher named S. Christian re-examined the evidence and raised concerns about how selection effects and the particular statistical tests employed might have influenced the result. The original team responded with their own 2020 paper, which they felt confirmed the existence of the structure, using the most reliable subset of the gamma-ray burst data, while also acknowledging clearly that definitive confirmation would require a substantially larger and more uniformly sampled catalogue than any currently available. That catalogue, they believed, could eventually be provided by a proposed European Space Agency satellite mission called the CEUS, the Transient High Energy Sources and Early Universe Surveyor. But that story belongs to the later chapters of this account. What is important to understand, standing here in the middle of the discovery's history, is the nature of where the science is. This is not a situation in which scientists have found and mapped a definite structure the way they mapped the Sloan Great Wall using millions of photographed galaxies. This is a situation in which scientists have found a statistical signal in the distribution of energetic events that they cannot directly explain by any natural process that does not involve an extraordinary concentration of matter, and that statistical signal is strong enough that it cannot be dismissed outright, but not yet strong enough that it can be declared settled. The Hercules Corona Borealis Great Wall is a candidate, the best candidate we currently have for the largest structure in the observable universe, supported by multiple independent analyses and multiple statistical tests, but still a candidate. Science is at its most honest in that condition, and the scientists working on this problem have largely maintained that honesty even as the stakes of the conclusion grow larger the longer the signal persists. Those stakes deserve to be made explicit. If the Hercules Corona Borealis Great Wall is real, if there truly is a concentration of matter, approximately 10 billion light-years across, sitting in the direction of those two ancient constellations, then the far implications for cosmology are profound in specific, concrete ways. The first implication is the one already touched upon, that the cosmological principle, the foundational assumption of the standard cosmological model, is violated at this scale in a way that the model does not predict and cannot naturally accommodate. Structures of this size should not exist. The theoretical limit on coherent cosmic structure under lambda cold dark matter, the scale at which the universe should become statistically uniform, is approximately 1 billion light-years. The wall, if real, is at minimum 6 to 8 times larger than that limit. The universe cannot violate its own physics. So either our understanding of those physics needs revision, or the wall is not what it appears. The second implication follows directly from the first. If the universe can build a 10 billion light-year structure, the mechanism by which it did so must be different from the mechanism we currently describe. And since that mechanism, the amplification of small initial density variations by gravity over cosmic time, governed by the known properties of dark matter and dark energy and ordinary matter, is the same mechanism that produces all the structure we see in the universe, a revision of that mechanism would not be a small adjustment. It would ripple through our entire understanding of how the cosmos evolved from the smooth, hot state of the early universe to the richly structured cosmos we inhabit today. There is also a third implication, more subtle but perhaps equally important. If the wall exists, it sits at distances corresponding to a time when the universe was roughly 3.5 to 4 billion years old. That means the matter in the wall was concentrated into a coherent, large-scale structure before the Earth existed, before the Sun existed, before the Milky Way had assembled into anything resembling its current form. And it had to have gotten that way in the time available, roughly 3.5 billion years from the Big Bang to that epoch. The Standard Model, as we will explore more fully later in this video, says that is not enough time. Gravity works, but it does not work that fast at those scales. To assemble a 10 billion light-year structure in 3.5 billion years would require either that the initial density variations were far larger than the cosmic microwave background data shows, or that some other mechanism was at work that our current models do not include. Either possibility is, in the careful vocabulary of cosmology, an extraordinary claim. Extraordinary claims, of course, require extraordinary evidence, and the nature of the evidence available for the Hercules Corona Borealis Great Wall is, as the scientists themselves have consistently acknowledged, statistical rather than direct. The wall has not been photographed. Its component galaxies have not been individually catalogued. Its dark matter has not been mapped. It is a pattern in a catalogue of gamma-ray bursts, and while that pattern is compelling, it is also subject to the limitations of the method that produced it. Gamma-ray bursts are rare and unevenly sampled. The catalogue, though rich by the standards of high-energy astrophysics, is small by the standards of galaxy surveys. The statistical methods used to detect the clustering, though standard and well-validated, are sensitive to the assumptions built into them. What would it take to move from statistical inference to something closer to direct confirmation? More bursts. First of all, a catalogue, an order of magnitude larger than what Swift had compiled by 2013, sampling the sky more uniformly and more deeply, reaching fainter bursts that might have been missed, and bursts at the precise redshifts of interest in regions of sky that the original catalogue had observed less thoroughly. That would allow the statistical analysis to be performed on a dataset robust enough that the choices of method and bin size would matter much less, and it would allow, potentially, for additional tests of whether the clustering is a projection effect, whether bursts that appear clustered on the sky are actually distributed through a range of depths that would make them tracings of several separate structures that happen to overlap when projected onto a two-dimensional map rather than members of a single coherent physical structure. Beyond the gamma-ray bursts themselves, confirmation might eventually come from instruments capable of detecting the galaxies themselves at those distances. The James Webb Space Telescope, the most capable infrared observatory ever built and placed in operation, has already demonstrated an ability to detect galaxies at redshifts comparable to those of the Hercules Corona Borealis Great Wall. A targeted survey of the relevant region of sky with sufficient depth might, in principle, begin to reveal whether the galaxy distribution in that direction shows an excess consistent with a physical concentration of matter, though this would require an enormous observational investment and would still face the difficulty that individual galaxies at those distances are faint, numerous, and difficult to disentangle from one another without extensive spectroscopic follow-up. What is becoming possible now, at the frontier of observational cosmology, would have been genuinely out of reach in 2013. The same is true of the artificial intelligence-driven methods of cosmic mapping that are beginning to transform the field. The ESA Euclid mission, which released its first substantial data set in March of 2025, including maps covering roughly 2,000 square degrees of sky. Approximately 14% of its planned total survey area has pioneered the use of machine learning tools to classify galaxies, identify gravitational lenses, and characterize the large-scale structure of the universe with a speed and throughput that no human team could match. Euclid's full cosmology data release is expected in the autumn of 2026, and it is expected to transform our picture of the cosmic web in the same way that the Sloan Digital Sky Survey transformed it in the early years of this century by adding a new order of magnitude to what we have mapped and measured. Whether Euclid's data will have anything to say directly about the Hercules Corona Borealis Great Wall depends on whether its surveying strategy covers the relevant region of sky at the relevant depths, and the full picture will only emerge as the mission proceeds. For now, the wall sits in the data the way all unresolved scientific questions sit, insistently refusing either to explain itself fully or to go away. The signal is there. The statistical analyses are there. The papers have been published, peer-reviewed, challenged, defended, and challenged again. The scientists who found it are still working on it, still refining the catalogue, still applying new methods to the existing data and to new data as it becomes available. And the scientific community as a whole has arrived at a posture of genuine, productive uncertainty, taking the results seriously enough to continue investigating, while honestly acknowledging that it is not yet confirmed in the way that a direct survey of the relevant galaxies would confirm it. What gives the story its particular force, and what ensures that it is more than an interesting statistical puzzle, is the scale of what is at stake if the wall turns out to be real. A statistical anomaly in a gamma-ray burst catalogue is one thing. A structure 10 billion light-years across that should not exist within the known laws of cosmology is something else entirely. The difference between those two descriptions is the difference between a puzzle and a crisis, and whether the Hercules Corona Borealis Great Wall represents a puzzle or a crisis for modern cosmology is precisely what the scientific investigation of the last decade has been attempting to determine, without yet arriving at a final answer. That investigation is about to take us deeper into the specific physical reasons why the wall's existence is so difficult to accommodate, and into the instruments and observations that are now in the years we are living through, in the discoveries that are still arriving, beginning to illuminate the darkest corners of the question. The most uncomfortable question the Hercules Corona Borealis Great Wall raises is not whether it exists, it is whether the universe had enough time to build it. That question cuts deeper than the statistical debate over gamma-ray burst clustering, deeper than the methodological disputes over selection effects and catalog biases, because it reaches into the physics of how the universe forms its structures at all, and what the answer implies about whether those physics are complete. To understand the time problem fully, you need to start at the beginning. Not the beginning of the discovery, but the beginning of everything, the first moments after the Big Bang, when the universe was a hot, dense, nearly featureless sea of energy and matter in a state of such extraordinary compression that the concepts we use to describe the ordinary cosmos barely apply. In those first fractions of a second, the universe was not transparent. Light could not travel freely through it, because the matter was so tightly packed and so energetically charged that photons were constantly colliding with electrons and protons, absorbed and re-emitted almost instantly, trapped in a fog so thick that the universe glowed from within, but could not be seen through from any point within it. The universe at that stage was not dark. It was blindingly bright in every direction simultaneously, a perfect, featureless, opaque furnace. What seeded the structure we see today was a kind of imperfection in that furnace, not a large imperfection, not something you could have detected with any instrument we have ever built if you had somehow been present in those first moments. The variations in density that existed in the early universe were tiny departures from perfect uniformity on the order of 1 part in 100,000. Some patches of space contained very slightly more matter than average. Others contained very slightly less. These variations appear to have originated from quantum processes during the period of cosmic inflation, the extraordinary, exponential expansion of space that cosmologists believe occurred in the first tiny fraction of a second after the Big Bang, stretching microscopic quantum fluctuations to macroscopic scales and imprinting them on the fabric of the cosmos as the seeds of all future structure. Those seeds were almost unimaginably small, in their effect on the universe's density. But gravity, as noted earlier, is patient, and it is relentless. The regions that were slightly denser than average began, slowly at first, and then, with gathering momentum, to pull in matter from their surroundings. The attraction was weak to begin, with the density contrast was, after all, only 1 part in 100,000, but each small addition of matter made the region slightly more massive, which made it slightly more attractive, which drew in more matter, which made it more massive still. This self-reinforcing process is called gravitational instability, and it is responsible for every large-scale structure in the observable universe, every galaxy cluster, every filament of the cosmic web. It is a process that works reliably and predictably under the laws of gravity that Newton first formalized in the 17th century and that Einstein refined in the 20th. But it works on timescales that are governed by those same laws, and those timescales are not arbitrary. They are specific, calculable, and finite. The crucial point is this: gravitational instability is not fast. Given the density contrasts that existed in the early universe small, as measured by the cosmic microwave background, and given the competing effects of cosmic expansion, which was working to pull matter apart even as gravity was trying to pull it together, the growth of structure proceeded at a well-defined rate. Structures grew from the bottom up. Small clumps of matter formed first, then merged into larger ones, which merged into still larger ones, which eventually assembled into the galaxy clusters and superclusters and great filaments of the cosmic web we observe today. This hierarchical assembly took time. The first stars ignited roughly a few 100 million years after the Big Bang. The first galaxies assembled over the next billion years. Galaxy clusters began to emerge after a few billion years, and the great filaments and sheets of the cosmic web, the structures hundreds of millions of light years in scale, were still assembling well into the universe's middle age, and in some sense continue to assemble today. The time scale for this process depends, in specific and calculable ways, on the scale of the structure involved. Small structures form quickly because the density contrasts on small scales are large. They exceed the background density by a significant factor, and gravity can act efficiently across short distances in short times. Large structures form slowly because the density contrasts on large scales are small. The more you average over a large volume, the closer the density comes to the cosmic mean, and because gravity must act coherently across enormous distances to pull such volumes together. At the scale of a galaxy cluster, roughly tens of millions of light years, gravity has had time to fully assemble the cluster and bind it gravitationally. At the scale of a supercluster, hundreds of millions of light years, gravity has had time to begin organizing matter into flows and sheets, but not yet to fully bind it. Superclusters are not gravitationally bound objects in the way clusters are, but rather large-scale patterns in the matter distribution that are still in the process of forming. At the scale of 1 billion light-years, the universe has barely begun to differentiate. The density contrasts are so small that what we see is nearly, though not quite, uniform. And at the scale of 10 billion light-years, the cosmological principle should simply be true. The universe should be completely smooth, because gravity has not had enough time to create meaningful structure at that scale. This is not a vague claim. It is a precise prediction of the lambda cold dark matter model, verified by the same computer simulations that correctly reproduce the cosmic web at all smaller scales. Those simulations start with the density variations measured in the cosmic microwave background, apply the known laws of gravity, dark matter dynamics, gas physics, and dark energy, and evolve the universe forward from the Big Bang to the present day. The results match the observed cosmos with remarkable fidelity at scales up to a few 100 million light-years. At larger scales, the simulations predict smoothness and the observations, until the discovery of the gamma-ray burst clustering in the direction of Hercules and Corona Borealis, were consistent with that smoothness. The specific time problem for the Hercules Corona Borealis Great Wall can be stated simply. The wall, if it exists, appears to sit at redshifts between approximately 1.6 and 2.1. At those redshifts, the light we are receiving was emitted when the universe was roughly 3 to 4 billion years old. That means that whatever concentration of matter produced the clustering of gamma-ray bursts we observe had to have assembled, or at least begun to assemble into something coherent at that scale within the first 3 to 4 billion years of cosmic history. But under the Standard Model, the density variations that were present in the early universe were far too small to generate a coherent structure 10 billion light-years across in that amount of time. The universe would need the density contrasts on those scales to be dramatically larger than what the cosmic microwave background shows, or the growth of structure would need to proceed dramatically faster than the Standard Model predicts, or some combination of both. None of those options is available within the Standard Framework. The Standard Framework says it cannot happen, and yet, apparently, something happened. This is what makes the Hercules Corona Borealis Great Wall so genuinely difficult for cosmologists. It is not merely a very large structure. It is a very large structure at a time when the universe was too young to have built something that large. The combination of scale and epoch is what turns a statistical anomaly into a potential crisis. If the wall were as large, but located at much lower redshift, if it were a feature of the universe as it is today, or as it was 5 or 6 billion years ago, it would still be large enough to challenge the cosmological principle, but the time problem would be somewhat less acute, because gravity would have had more time to work. The fact that it appears to sit at high redshift in the relatively young universe adds an additional layer of difficulty that no simple adjustment to the Standard Model can easily resolve. What adjustments might, in principle, resolve it? This is where the scientific discussion becomes most interesting and most speculative, and it is important to distinguish carefully between proposals that are well-motivated extensions of known physics and proposals that are more dramatic departures. The first category includes the possibility that the primordial density fluctuations, the seeds imprinted during inflation, were not as smooth and Gaussian as the Standard Model assumes. Standard inflationary models predict that the fluctuations should follow a near-perfect Gaussian distribution, meaning that large fluctuations should be exponentially rare. But not all models of inflation are identical. Some extended models predict departures from Gaussianity on specific scales, concentrations of power, at particular wavelengths of density variation that could, in principle, enhance the growth of structure on those scales without contradicting the overall success of the Standard Model at smaller and larger scales. If the density fluctuations on scales of a few billion light-years were larger than the simple inflationary model predicts, structure on those scales could have grown faster, and the existence of something like the wall in the relatively young universe would become less improbable. The problem with this explanation is that the cosmic microwave background imposes tight constraints on how non-Gaussian the primordial fluctuations can be. The Planck satellite measured the statistics of the microwave background with extraordinary precision, and the results were consistent with the simple Gaussian prediction to a degree that left very little room for the kind of non-Gaussianity that would significantly speed up large-scale structure formation. Not zero room. The constraints are not infinitely tight, but the modifications allowed are modest, and it is not clear that modest modifications would be sufficient to account for something as extreme as the wall. A second category of proposed explanations involves modifications to the behavior of dark matter. The standard model assumes cold, dark matter particles that were moving slowly when the universe was young, allowing them to cluster efficiently under gravity from very early times. Various alternatives have been proposed over the years. Warm dark matter, which consists of slightly faster moving particles that smooth out structure on small scales but leave large scales unchanged. Fuzzy dark matter, which behaves like a quantum wave rather than a classical particle on the scales of dwarf galaxies. Self-interacting dark matter, in which dark matter particles interact with each other through some new force. Most of these alternatives were proposed to address different problems. Discrepancies between the predictions of standard cold dark matter and the observed properties of small galaxies and dwarf satellite galaxies rather than to explain anomalously large structures. And for the most part, they do not significantly alter the behavior of dark matter on the billion light-year and larger scales relevant to the wall. Dark matter, in all of its proposed forms, still clusters under gravity on those scales at roughly the rate the standard model predicts. A third category is more radical: modifications to the laws of gravity themselves. General relativity. Einstein's description of gravity as the curvature of space-time produced by mass and energy has been tested with extraordinary precision across an enormous range of scales, from laboratory measurements to the orbits of binary pulsars to the behavior of the expanding universe as a whole. It has passed every test, but there are theoretical reasons to consider whether general relativity might need modification on the very largest cosmological scales, whether the way gravity behaves when acting coherently across billions of light-years might differ subtly from the behavior predicted by Einstein's equations. Some alternative theories of gravity predict enhanced clustering on large scales, which would allow structure to grow faster and reach larger scales in less time than the standard model allows. These theories have not been confirmed, and many of them introduce problems elsewhere that Einstein's original equations do not have. But they remain an active area of theoretical investigation, and the Hercules Corona Borealis Great Wall provides, for those working in that area, a concrete observational puzzle that modified gravity theories might need to accommodate. There is a fourth possibility that is perhaps the most sobering of all, that the wall is not a single coherent physical structure, but a projection, effect, a chance alignment of several smaller, physically separate concentrations of matter that happen to lie along roughly the same line of sight, creating the appearance of a single enormous structure, when in fact the individual components would each be more modest in scale and therefore easier to accommodate within the standard model. This is not an implausible concern. The deep universe is not easy to navigate. At the distances where the wall appears, we are looking along a line of sight that passes through billions of light-years of space, and several physically distinct concentrations of galaxies could, if they happened to be distributed in the right way, project onto the same patch of sky at similar redshifts without being connected to each other in any physical sense. Disentangling a genuine coherent superstructure from an accidental alignment of separate structures is precisely the kind of problem that requires either a much denser sampling of the region, many more gamma-ray bursts, each with precise positions and redshifts, or direct observation of the galaxies themselves in sufficient numbers and with sufficient positional information to map the three-dimensional distribution of matter. This projection concern is one of the reasons that the question of the wall's existence has remained open despite more than a decade of investigation. The gamma-ray burst catalogue, even with the additions from Batsi and Fermi that the 2015 follow-up study incorporated, does not provide enough data points to confidently reconstruct the three-dimensional structure of the matter distribution in that region. The bursts tell us that something is there. They do not yet tell us, with sufficient precision, exactly what it is, whether it is one coherent object or several separate objects that happen to overlap from our viewpoint. The scientific community that has engaged most seriously with the wall has, to its credit, kept both possibilities in clear view throughout. The papers from Horvath and his colleagues have consistently acknowledged that the projection interpretation cannot be ruled out. The papers from those who have challenged the original result have consistently acknowledged that the clustering signal, while potentially explainable by selection effects or statistical biases, has not been definitively explained away. The debate has been conducted honestly, with both sides holding their conclusions with the appropriate degree of tentativeness, neither dismissing the wall as nonsense, nor claiming it as proof that cosmology is broken. This is science at its best, even when the process is slower and more uncertain than anyone would prefer. One particularly interesting contribution to the debate came in 2025 from a team at Cambridge University and several European collaborators working with a powerful computer simulation called Flamingo, specifically a very large version of that simulation known as Flamingo 10K. This simulation was among the largest cosmological simulations ever run, designed to model the evolution of structure across an enormous volume of the universe under the assumptions of the standard lambda cold dark matter model. The Cambridge team used this simulation to address a specific question: how often do large-scale patterns, not necessarily the wall itself, but patterns of comparable or somewhat smaller angular extent, arise by chance in a universe governed by the standard model? Their conclusion, published in monthly notices of the Royal Astronomical Society letters, was that such patterns are more common than had previously been assumed. Structures like the giant arc, a curved arrangement of galaxies approximately 1 billion light-years in length, identified in 2021, and the Big Ring, an approximately circular arrangement of galaxies at a diameter of around 1.3 billion light-years, announced in 2024, both of which had been cited as potential violations of the cosmological principle, appeared to arise naturally in the Flamingo simulation without requiring any departure from the standard model. The simulation showed that on scales of roughly 1 gigaparsec, patterns that look visually striking and statistically unusual when projected onto the sky are actually consistent with what lambda cold dark matter predicts. This was an important result, and it deserves careful consideration in the context of the wall. If the standard model can produce 1 gigaparsec patterns more easily than had been thought, then perhaps the cosmological principle is not quite as strict a constraint at those scales as the conventional wisdom held. And if the permitted scale for coherent patterns is larger than the traditional limit of approximately 1 billion light-years, which the flamingo result appeared to suggest, then some of the statistical alarm around structures like the giant arc and the Big Ring may be somewhat overstated. The universe may be able to accommodate somewhat larger patterns than the simplest reading of the cosmological principle would suggest, without requiring any departure from the standard model. But, and this is a crucial caveat, the flamingo result applied to structures in the range of 1 gigaparsec. The Hercules Corona Borealis Great Wall, in the estimate of its discoverers, is approximately 3 gigaparsecs in its original estimate, and potentially 4 to 5 gigaparsecs in the revised 2025 analysis. The Flamingo simulation did not demonstrate that 10 billion light-year structures arise naturally in lambda-cold dark matter. It demonstrated that 1 billion light-year patterns do. The gap between what the simulation showed and what the wall would require is still enormous, roughly a factor of 3 to 5 in linear scale, which translates to a factor of 25 to 125 in volume. The Flamingo result provides some comfort at the smaller scales, but does not reach the scale of the wall itself. What Flamingo did demonstrate, and what is genuinely useful, is that the threshold between consistent with the standard model and inconsistent with the standard model is not a sharp cliff, but a gradient. The universe does not suddenly become perfectly uniform at exactly 1 billion light-years. The transition is gradual, and the statistical significance of anomalies depends sensitively on exactly where you are along that gradient and on what statistical tools you use to assess the anomaly. This means that a careful treatment of the wall's statistical significance requires not just asking whether the clustering is unlikely under the assumption of perfect uniformity, but asking how unlikely it is given the full range of structure that the standard model actually predicts, including the structures that the Flamingo result showed are more common than once believed. When the comparison is done properly, the wall remains an extreme outlier. But exactly how extreme, and what that extremity implies for the status of the cosmological principle, depends on the details of the analysis, in ways that researchers continue to work through. The 2025 reanalysis of the Hercules Corona Borealis Great Wall by Horvath and colleagues added a new dimension to this discussion. Using an expanded catalogue of 542 gamma-ray bursts from the Fermi satellite, a substantially larger dataset than had been available in 2013, the team applied new scanning methods to reassess the extent and position of the clustering. Their results suggested that the structure might be both larger and closer to Earth than the original study had indicated, with the clustering potentially extending to redshifts as low as approximately 0.33, much lower than the original range of 1.6 to 2.1, and reaching a total longitudinal extent that could approach 15 billion light-years or more. The transverse extent was estimated at approximately 7.2 billion light-years. If these revised figures are accurate, the wall would be even more difficult to accommodate within the standard model than the original discovery suggested, and the time problem would be compounded rather than alleviated, because the structure, extending to lower redshifts, would have to have begun assembling even earlier in cosmic history, while also having grown to an even larger final size. The revised analysis also suggested that the wall might not be a single monolithic structure but rather a complex, elongated system of interconnected galaxy concentrations, a vast network of filaments and sheets extending across a region of space so large that it challenges our ability to think about it as a single object at all. This is consistent with how cosmologists think about very large structures in general. The cosmic web is not composed of isolated blobs, but of continuous, interconnected patterns of matter, and a region as large as the wall, if it is real, would inevitably be a region where many individual clusters and filaments overlap and connect rather than a single uniform mass. But that very complexity makes it harder to characterize and harder to confirm. Each subcomponent needs to be studied individually, and the question of whether they are all physically connected or merely appear connected from our vantage point becomes even more pressing. One of the most striking aspects of the revised 2025 analysis was its implication for the structure's relationship to the theoretical predictions of the Standard Model. The original discovery was already in tension with those predictions. The revised and potentially larger structure makes that tension sharper, and the researchers themselves were explicit in pointing to the CEUS, the transient high-energy sources and early universe surveyor, as the instrument that would be needed to make genuine progress on resolving the question. The CEUS is a proposed ESA mission designed to detect gamma-ray bursts with dramatically higher sensitivity and sky coverage than SWIFT or Fermi, enabling the construction of a catalogue, potentially an order of magnitude richer than anything currently available. With such a catalogue, the clustering analysis could be performed with the kind of statistical power that would make the conclusions genuinely robust, less sensitive to the specific choices of method and bin size that have allowed the debate to remain open, and capable of mapping the three-dimensional structure of the wall's candidate region with enough resolution to distinguish between a coherent superstructure and a projection of physically separate concentrations. The fact that the CEUS is a proposed mission not yet approved for launch, with a target date that remains in flux, means that definitive resolution is still some years away, even if everything proceeds optimally. The scientific community is in a position that is familiar from the history of astronomy. The instruments needed to settle the question are known and are being developed or planned, but the question itself must remain open in the meantime. This is not a comfortable position for anyone involved. The wall has been a candidate structure for more than a decade now. The debate has generated dozens of papers, engaged researchers across multiple countries and institutions, and absorbed a significant amount of scientific attention. And yet the fundamental question, is it real, remains genuinely unanswered. There is something instructive in that situation, and it goes beyond the specific case of the Hercules Corona Borealis Great Wall. The universe's largest scales are simply harder to study than its smaller scales in ways that are not merely technical but fundamental. At small scales, the scale of a star, a planetary system, a galaxy, we can observe many individual objects, characterize their properties in detail, and build statistical conclusions on large samples. At the scale of galaxy clusters, we can still work with hundreds or thousands of individual clusters, map their properties, measure their masses through gravitational lensing, and compare the results to simulations with confidence. But at the scale of the wall, 10–15 billion light-years, the observable universe contains only a handful of regions this large, and we can only observe each from a single vantage point, our own. We cannot fly around the wall and look at it from the other side. We cannot observe another universe to see how common such features are in the broader statistical ensemble of possible cosmic histories. We are limited, fundamentally, to the data we can gather from our single position in space and time, looking out in all directions into a universe that extends far beyond what we can see. That limitation is not a failure of science. It is a feature of the specific situation in which science finds itself at this moment in history, equipped with instruments of extraordinary capability, but still constrained by the finite speed of light and the finite age of the universe in ways that set an absolute outer boundary on what can be known. Within those constraints, the investigation of the Hercules Corona Borealis Great Wall is a model of how science engages with difficult, high-stakes questions, carefully, honestly, with appropriate tentativeness and rigorous methodology, neither claiming more than the evidence supports, nor dismissing what the evidence genuinely shows. The instruments being developed, instruments that will probe the deep universe with greater sensitivity and larger samples than anything built before, represent the next chapter of that investigation. And the answers they produce, when they come, will matter, not just for the specific question of the wall's existence, but for the much larger question of how well our best models of the universe actually describe the universe as it is. The instruments are arriving. That is not a metaphor or a figure of speech. The telescopes and satellites and survey systems that the scientific community has been building and planning and arguing over for years are now beginning to deliver what they promised. And the picture they are sending back from the deep universe is richer and stranger and more detailed than anything that existed when Istvan Horvath and his colleagues first published their gamma-ray burst analysis in 2014. We are living at this precise moment in the history of astronomy through a transformation in our ability to see the large-scale structure of the cosmos that is comparable in its eventual significance to what happened when the first redshift surveys turned the flat map of the sky into a genuine three-dimensional chart of the universe. The difference is that this time we know, at least in rough outline, what we are looking for, and we know that somewhere out in the direction of Hercules and Corona Borealis, the data is either going to confirm the most extraordinary structure ever identified, or it is going to dissolve it into something that fits more comfortably within the known laws of cosmological physics. Either answer matters enormously, and either answer is now, for the first time, genuinely within reach. The James Webb Space Telescope has already contributed something significant to this story, though not in the way that some might initially expect. Webb was not designed to search for the Hercules Corona Borealis Great Wall specifically. Its primary scientific missions involve the atmospheres of exoplanets, the formation of the first stars and galaxies, and the properties of extremely distant objects across many domains of astrophysics. But in May of 2026, researchers led by a team at the University of California, Riverside, published in the Astrophysical Journal what they described as the most detailed map of the cosmic web ever made. Using data from the Cosmos Web Survey, the largest program carried out with the James Webb Space Telescope to date, covering roughly half a square degree of sky with near-infrared imaging of extraordinary depth, the team traced the large-scale structure of the universe across nearly 14 billion years of cosmic history, extending their mapping to redshifts of approximately 7, meaning a time when the universe was only about 700 million years old. The cosmic web they mapped was more complex, more intricate, and more richly structured than anything the previous generation of telescopes had revealed. What Cosmos Webb showed, in practical terms, was how dramatically the new instrument's capabilities exceeded those of its predecessors. The Hubble Space Telescope had previously been used to study portions of the same region of sky, and what had appeared in Hubble's data as single, relatively simple structures resolved, in Webb's infrared light, into multiple distinct concentrations of galaxies with complex internal organization. Features that had been smoothed over by Hubble's lower sensitivity protoclusters, filaments, sheets of galaxies at high redshift emerged with a clarity that researchers described as genuinely revelatory. Bahram Mobasher, a distinguished professor at the University of California, Riverside, who led the team that produced the map, noted that what used to look like a single structure in older data was now seen to be a collection of many distinct and identifiable features. The jump in resolution, he said, was truly significant, and it opened access to an era of the universe's history that had been essentially out of reach before Webb began operations. This matters for the story of the Wall in a specific way. Cosmos Webb did not directly map the region of sky where the Hercules Corona Borealis Great Wall appears. It covered a different portion of the sky, chosen for different scientific reasons. And the Wall's candidate region is far too large for any single pointed survey to encompass directly. But what Cosmos Webb established is a proof of concept that Webb can detect galaxies at the redshifts where the Wall appears, can resolve individual structures within dense concentrations at those distances, and can produce maps of the cosmic web that are detailed enough to meaningfully distinguish between different physical configurations of matter. Future Webb surveys pointed at the Hercules Corona Borealis region, potentially combined with spectroscopic follow-up from ground-based facilities, could, in principle, begin to reveal whether the concentration of matter implied by the gamma-ray burst clustering is visibly present in the galaxy distribution, whether the galaxies themselves are there, organized in the ways the Wall hypothesis would predict. Rather than simply absent or uniformly distributed, the European Space Agency's Euclid mission adds another layer to this emerging picture. Euclid launched in July of 2023 and began its scientific survey operations shortly thereafter, covering large areas of the sky with a combination of optical and near-infrared imaging and slitless spectroscopy that allows it to characterize the shapes and redshifts of hundreds of millions of galaxies at once. In March of 2025, the mission released its first substantial data set, comprising observations of roughly 2,000 square degrees of sky, approximately 14% of the total area. Euclid will eventually survey, along with the first results from a novel combination of artificial intelligence and citizen science that had classified more than 380,000 galaxies and identified approximately 500 gravitational lens candidates in that data alone. The mission's full cosmology data release is expected in the autumn of 2026, when observations from multiple passes across the deep field regions will be combined to produce a map of large-scale structure that will, in its sheer volume and depth, surpass every galaxy survey previously conducted. Euclid's design is particularly well suited to addressing questions about the cosmological principle and the largest scales of cosmic structure. Its wide field of view allows it to map enormous volumes of space simultaneously, capturing the full extent of superclusters and great walls in a single survey sweep, rather than the patchwork of individual pointings that older telescopes required. Its photometric redshift measurements, estimating galaxy distances from the colors of their light rather than from time-consuming spectroscopic observations, allow it to process galaxies in enormous numbers, building up the statistical samples needed to detect clustering at the scales where the cosmological principle should hold. And its spectroscopic mode, though covering a smaller fraction of the sky, provides precise distance measurements for the galaxies it observes, enough to begin constructing three-dimensional maps of cosmic structure at scales that overlap with the regime where the wall appears. Whether Euclid will survey the specific region of sky occupied by the Hercules Corona Borealis wall in sufficient depth to address the question of the wall's existence depends on the details of its scanning strategy, which has been optimized for overall cosmological science rather than for this specific target. But the general principle is clear. A survey that maps hundreds of millions of galaxies across a third of the sky at redshifts extending well into the range where the wall appears will have something to say about whether the large-scale structure in that part of the universe is consistent with the wall hypothesis or with the Standard Model's prediction of uniformity. Euclid's full data release in 2026 will be one of the most scientifically significant events in observational cosmology in a generation, and the implications for the wall, whatever they turn out to be, will be part of that significance. And then there is the CEAS. Of all the instruments that researchers working on the Hercules Corona Borealis Great Wall have pointed to as the key to resolving the question, the CEAS occupies a special position, not because it will map galaxies directly, but because it will do exactly what the original discovery required, and do it far better. It will detect gamma-ray bursts in vastly larger numbers and with dramatically greater sky coverage and sensitivity than any instrument that has come before. The CEAS, the Transient High Energy Sources and Early Universe Surveyor, is a mission proposed to the European Space Agency, designed specifically to exploit the gamma-ray burst population as a cosmic tool for probing the early universe. Its wide-field detectors, capable of monitoring a significant fraction of the sky simultaneously, would detect gamma-ray bursts at rates far exceeding Swift or Fermi, and its onboard infrared telescope would allow it to immediately characterize each burst's redshift, its distance, without waiting for ground-based follow-up. The expected yield from the CEAS, if the mission is launched, would transform the gamma-ray burst catalog from the kind of sample that Horvath's team was working with a few hundred bursts total across the full sky at all redshifts, with perhaps 30 or 40 in the redshift range of interest, into a catalog of thousands of bursts with precise positions and distances distributed across the sky with the statistical uniformity needed to make genuine large-scale structure measurements. With that kind of data, the clustering analysis that produced the wall's detection could be performed not as an exercise at the frontier of what the available sample allows, but as a robust measurement with small enough statistical uncertainties to be definitive. If the wall is real and as large as the data suggests, the clustering would appear in the CEAS-era catalog with overwhelming statistical clarity. If it is a projection effect or a consequence of selection biases in the existing catalog, a much larger and more uniformly sampled catalog would reveal that the clustering dissolves when the full population is seen. Either way, the question that has been open since 2013 would have, at last, a genuine answer. The fact that the CEAS has not yet been formally approved for launch, that it remains a proposed mission competing for funding and scheduling within ESA's program, introduces a degree of uncertainty about when that answer will come. Space missions take years to build and launch and begin returning data, and the process of selection and approval adds additional years before construction even begins. Researchers working on the wall have expressed confidence that the Soyuz, or something very much like it, will eventually be built, because the scientific case for a mission in this class extends well beyond the Hercules Corona Borealis Great Wall to encompass a wide range of high-energy astrophysics and early universe science. But science does not proceed on timelines that anyone controls entirely, and the history of astronomy is full of missions that took longer than anticipated and produced results that arrived later than hoped. The willingness to work on long timescales to build instruments that will answer questions posed a decade or two earlier is one of the qualities that distinguishes observational astronomy from fields where experiments can be conducted more quickly. In the meantime, the investigation has not stood still. The artificial intelligence tools that Euclid has already deployed for galaxy classification represent a broader transformation in how large-scale structure is studied and characterized. Machine learning algorithms trained on large samples of galaxies with known properties can process survey data at speeds that no human team could match, identifying structures, measuring clustering statistics, and flagging anomalies in the distribution of matter with a consistency and thoroughness that removes many of the human judgment calls that have historically introduced uncertainty into structure measurements. These tools are still being refined and validated, and there are genuine questions about what biases they might introduce and how well their outputs can be trusted in the regimes where the underlying physics is uncertain. But the direction of travel is clear. The next generation of large-scale structure science will be conducted in partnership between astronomers and the machine learning systems they have built. And that partnership will allow the field to extract far more information from its data than was possible even a decade ago. The question of what the Hercules Corona Borealis Great Wall means, if it is real, has occupied cosmologists in a way that goes beyond the technical dispute over gamma-ray burst statistics. It sits at the intersection of observation and theory in a way that demands honesty from both sides, and it raises questions that are not merely scientific but epistemological, questions about what we can know from our single vantage point in space and time about a universe that extends far beyond what we can see. We have built our picture of the cosmos from observations made over a century from our one small planet, looking out in all directions but always from the same fixed location in space. The structures we have discovered, galaxies, clusters, superclusters, the cosmic web itself, are all inferred from the light that has managed to reach us, emitted at various times in cosmic history, carrying information about conditions in distant regions of space that we can never visit and have only observed from afar. At the largest scales, this limitation becomes acute in a very specific way. The observable universe is finite, bounded by the distance that light has had time to travel since the Big Bang, approximately 46.5 billion light-years in every direction from our position. Within that volume, there is only one example of each of the very largest structures. There is only one region of the sky in the direction of Hercules and Corona Borealis. There is only one potential Hercules Corona Borealis Great Wall. We cannot compare it to a statistical ensemble of similar structures drawn from many different regions of the universe the way we can compare, say, galaxy clusters, of which there are hundreds of thousands. The universe gives us only one shot at seeing what its most extreme features look like, and that single example has to carry all of the statistical weight of our conclusions about whether such features are consistent with our models or not. This is a deep epistemic limitation, and It is one that no amount of improved instrumentation can fully overcome, though better instruments can at least constrain the question more tightly by gathering more data about the one example we have. There is something humbling in that limitation. The universe is under no obligation to present itself in a form that is easy for us to study. It does not space its most interesting features conveniently close together or arrange its largest structures in ways that give us multiple copies to examine. It has one cosmic web, and we sit inside it, looking outward, trying to reconstruct its full architecture from the light that reaches our telescopes. The cosmic web, we have mapped the filaments and voids and clusters that the Sloan Digital Sky Survey and its successors have revealed, represents an achievement of extraordinary difficulty and extraordinary ingenuity, built up over decades by thousands of astronomers using instruments that range from modest optical telescopes on mountaintops to billion-dollar space observatories in orbit around the Sun. And even with all of that, the question of whether the universe contains a structure as large as the Hercules Corona Borealis Great Wall remains, after more than a decade of investigation, genuinely open. What the investigation has produced, even without a final answer, is a clearer map of what we do and do not know about the large-scale structure of the cosmos. We know that the cosmic web is real, and that it is organized in the ways the standard model predicts at scales up to a few 100 million light-years. We know that at somewhat larger scales approaching 1 billion light-years, the standard model's predictions have more uncertainty than was once assumed, and that patterns at those scales may be more common than the conventional reading of the cosmological principle suggested. We know that the gamma-ray burst data contains a clustering signal in the direction of Hercules and Corona Borealis that has persisted through multiple independent analyses and survived the most careful scrutiny that the scientific community has applied to it. And we know that if that clustering signal reflects a genuine physical structure, that structure is far larger than anything the standard model can easily accommodate, and its existence, at the epoch where it appears, poses a time problem that no minor adjustment to the standard framework can resolve. We also know, and this is worth saying clearly, that the Hercules Corona Borealis Great Wall has not been confirmed. It is a candidate structure, supported by statistical evidence that is compelling but not definitive, constrained by the limitations of the gamma-ray burst tracer method and the finite size of the available catalog. The scientists who have worked on it have been honest about those limitations throughout, and the scientific community as a whole has responded with the appropriate combination of serious engagement and healthy skepticism that the evidence deserves. This is not a case of fringe science being ignored by the mainstream. It is a case of mainstream science grappling with an extraordinary result in exactly the way it should, with rigor, with caution, with continued investigation, and with the willingness to be surprised. Being surprised is, in the end, one of the most important things that science allows us to do. The history of astronomy is a history of surprise. The discovery that the Earth moves around the Sun, which surprised everyone who had believed the opposite for their entire lives. The discovery that the Milky Way is not the entire universe, which surprised the generation of astronomers who had mapped the galaxy, believing they had mapped everything. The discovery that the universe is expanding, which surprised Einstein himself, who had included a mathematical term in his equations specifically to prevent that conclusion. The discovery that the expansion is accelerating, driven by an unknown form of energy that nobody had predicted and that still has no satisfying theoretical explanation. Each of these surprises was, at the time it arrived, deeply uncomfortable for the existing framework of knowledge. Each required revisions, sometimes minor, sometimes fundamental to the models that had seemed so secure. And each ultimately produced a richer and more accurate understanding of the cosmos than existed before the surprise arrived. The Hercules Corona Borealis Great Wall may be the next such surprise, or it may dissolve under better data into something more ordinary, a collection of separate structures that only appeared connected through the limitations of a small and imperfect catalogue. Either outcome is scientifically valuable. A wall that turns out to be a projection effect teaches us something important about the limitations of gamma-ray burst mapping as a tool for large-scale structure studies, and about how easily our eyes and our statistics can be deceived by patterns that look like structure but are not. A wall that turns out to be real teaches us something far more important, that the universe assembled something at a scale and in a time that our best models say it could not, which means our best models are incomplete in ways we do not yet understand, and the work of understanding them better has only just begun. There is a quality to that second possibility that goes beyond the merely scientific. The cosmos has been assembling its structures for 13.8 billion years without consulting us. It formed its first stars from the simplest elements, hydrogen and helium, scattered across the cooling universe in the minutes after the Big Bang without any guidance from the beings who would eventually develop the curiosity to ask how those stars came to be. It built its galaxies through the patient accumulation of gas and dark matter over hundreds of millions of years, long before anything on Earth could look up and wonder at the light those galaxies emitted. It organized its galaxy clusters and superclusters and cosmic web filaments through the slow, relentless operation of gravity across distances that dwarf human comprehension, and if it built something like the Hercules Corona Borealis Great Wall in the process, something 10 or 15 billion light-years across, assembled in the universe's first few billion years, it did so without any regard for whether the physics we had worked out would permit it. The universe does not need our permission to do what it does. That is not a trivial observation. It is the foundation of what science is. The recognition that the cosmos has its own behavior, its own rules, and that our job is to discover those rules through observation and inference and the testing of ideas against evidence, not to decree what the rules must be and then dismiss whatever does not fit. When the data shows something we did not expect, the appropriate response is not to explain it away before we understand it. The appropriate response is to look more carefully, gather more data, apply better tools, and follow the evidence wherever it leads, even when it leads somewhere uncomfortable, even when it leads somewhere that requires dismantling part of what we thought we knew. That is exactly what the astronomical community has done with the Hercules Corona Borealis Great Wall over the past 12 years, and it is what the CEOS and Euclid and the Webb telescope and all the instruments still being designed and built will continue to do in the years to come. The question of whether the wall is real remains open. The investigation of that question and of the larger questions about cosmic structure that it has brought into focus is very much alive. And we are at a moment, a rare and fortunate moment, when the instruments needed to move toward an answer are coming online, when the data is beginning to flow, when the maps are becoming richer and more detailed with every passing year. Stand outside on a clear night and look in the direction of Hercules and Corona Borealis, two constellations near the zenith in the northern summer sky, one named for the greatest hero of ancient Greece, the other for a crown left behind in the heavens. In that direction, somewhere between 9 and 10 billion light years away, and possibly stretching much farther than that, the data says there is something. A concentration of matter so vast that the light crossing from one end to the other would take longer to make the journey than the sun has left in its life. Something that the most sophisticated cosmological framework in the history of science struggles to accommodate within its predictions. Something that a team of astronomers found in a catalogue of gamma-ray bursts and have been unable to explain away for more than a decade. Something that the next generation of space observatories is being trained to examine with greater precision than has ever before been possible. The stars you see in those constellations are, of course, not part of the wall. They are nearby stars, members of our own Milky Way, positioned in that direction from Earth by the random arrangement of our galaxy's spiral arms. The wall, if it exists, is so far beyond them that the distance between us and the nearest of those stars is essentially nothing by comparison. A short step in a driveway, measured against the full width of a continent. The light we see from those constellations left its sources within a few thousand years of our own time. The light, whose pattern in a satellite's data revealed the candidate wall was emitted before the Earth existed, before the Sun ignited, before the solar nebula that would eventually become our planetary system had even begun to contract under its own gravity. The wall is not part of our sky in the way those constellations are. It is part of the deep fabric of the universe, the layer of reality that underlies everything we see, and that we are only beginning to learn to read. There is something both sobering and oddly comforting in that. Sobering because it reminds us of how little, still, we see of the full cosmos, how much lies beyond what our instruments can resolve, how much lies beyond what our theories can predict, how much the universe has done and continues to do in regions we will never observe, and at scales we can barely conceive. Comforting because it means the work is not finished. The questions are not answered. The sky still holds more than we know how to read, and the prospect of reading it better, of building the instruments and developing the methods and gathering the data that will eventually bring the wall's existence from the realm of compelling hypothesis to the realm of walls. Confirmed fact or resolved puzzle is a prospect that remains genuinely open. The universe has not yet given us its final answer. It has only given us the question, stated in the language of gamma-ray bursts and galaxy surveys, and the patient mathematics of statistical clustering, and we are still learning to ask it back, in a language precise enough to receive a reply. The silent weight of that 10 billion light-year something in the direction of two ancient constellations is not a burden. It is an invitation, and some of the finest scientific minds of this generation have accepted it and are building the tools to follow where it leads. When the answer finally comes, whether it confirms the wall as the largest structure in the observable universe or reveals it to be a pattern without a physical foundation beneath it, we will know something about the cosmos that we did not know before, and that knowing, however it resolves, will change how we see the dark between the stars. Rest easy, stargazer. The wall at the edge of everything will wait patiently while you sleep.